Hello, hello. It is time for lecture 22, 22, 22, 22. That's right, lecture 22, which is a very cool lecture, I have to tell you, because in lecture 21, we were just launching into nuclear stuff, right? Nuclear fusion, nuclear fission, radioisotope thermoelectric generators, nuclear power, those kinds of things, which are totally relevant to the famous equation E equals mc squared, right? E equals mc squared. As it turns out, E equals mc squared is a fascinating link to something really cool. And that is this thing about space and time. Now, we usually credit Albert Einstein with doing the key pioneer work to make this all happen. But if you understand physics at a level that everyone should sort of be familiar with how the universe works, it turns out that Einstein's E equals mc squared equation is just one piece of a huge and beautiful area of physics, which has direct relevance to our lives, not to mention cosmic significance. So let's go right to it and figure out what the story is. Okay, turns out the story is a little bit interesting. We start with Albert himself. Now, we've had some biographical information about Albert over the course of the semester already. In fact, there is a tremendous professor of physics, technically astronomy and physics. Most of modern astronomy is physics applied to the universe, but not all. In any case, astronomy professor Yervant Terzian at Cornell University, tremendously talented individual in his prime. He passed away not too long ago, but he is just a great guy. And he would, in his intro astronomy class, I actually didn't take this class because I didn't go to Cornell, alas, but he would, in his intro astronomy class, put a picture of Albert Einstein up on the screen. And he would say, "Who is this?" And everyone would say, "Einstein," because like he's like this iconic figure, right? Everyone knows what Albert Einstein looks like. He says, "No, in this class we call him Albert because Albert is our friend." Right? Basically, he's trying to humanize Albert Einstein, which is really true, right? He was a person just like all the rest of us. Now, that's really important for us to understand because when we're talking about the history of science and understanding physics, we should understand the people who are doing it. Why does it matter to them? And how did they look upon these things? How did they develop into the people that they were to make the discoveries that they did, right? That is of interest. That is of value. Here's the deal. Albert was a pretty smart guy, right? He was. In school, though, he was not the most favored students in the class compared to the other students that some others felt. Okay, not necessarily because he was, less intelligent or anything like that, but because he was not quite a conformist, and it kind of suffered as a result. Right? He actually talked about his own education as being like very frustrating to him, and he's like, it's a little wonder that anyone can think at all after they've gone through the public education system like I experienced. That's what he wrote in his later life. Of course, he experienced it in Germany in the 1870s, 1880s, and 1890s. So, that's a different perspective, but still holds, right? Education and teaching and learning. He felt that he was being inhibited in his creativity, right? I think that's also another cool thing that I want to keep that in mind for, because Albert Einstein's story about relativity and equals mc squared and stuff like that is a story of scientific creativity. A lot of times, people in non-scientific fields say that, well, physics is all about non-creativity, right? Physics is about following rules and things like that, right? You just have a series of things that you have to follow all the time. That's just how you have to do things. Of course, nothing could be further from the truth. You know how this goes, right? The gathering of facts and analyzing them as data, distilling out the laws of nature, then hypothesizing as to why these laws are there, and then making predictions, if your hypothesis is true, that can be either confirmed or otherwise falsified, right? At every step, there is creativity. At every step, there are ways. How might you create better instrumentation to gather data? How might you organize facts to understand what you're trying to achieve? How might you express your laws of nature? Would it be algebra? Would it be calculus? Would it be some other conceptual principle, right? In your hypotheses, you have to go from here, right? These rules, usually mathematically based, to something like why. Then you have to come up with predictions and experiments, ways to test those predictions. At every step, there is a creativity, a creative process that's absolutely necessary. And so what Albert Einstein did was basically going from the data into the laws, into the hypotheses. This was the area that he was most creative and most valuable. He made predictions as well, and then worked with other people over time to confirm or falsify them. That is Albert Einstein's story. And he felt that, if he just memorized facts and he learned things and solved tests well in puzzles and things like that, that wasn't really contributing to his interest or ability to do science or anybody's ability to be creative about how to fix the world, right? Or how to fix or figure out the world, for that matter. Anyway, he was a smart guy, no question about it. And as a result, he was able to get through school without too much difficulty. But again, he was never the top student. Really, he was a good student, but never the top student. And what happened was that around 1901, so this guy is 22 years old, he's graduated from the MIT of Switzerland. And many people say the MIT of all of Europe, right? It's called ETH, ETH in English, in Switzerland. Very, very talented guy. He went to school there and he was going to ETH or ETH for graduate school. Okay, he graduated from college and he was there and he wanted to do a PhD thesis as a graduate student. But he couldn't find an advisor to approve his project to begin with. His project was too revolutionary or perhaps too creative or not mainstream enough, basically. So he was like, that's kind of a bummer. So he was kind of bummed about that. But by around 1903, he was able to find such an advisor to help him do stuff. And it turned out that his thesis project, his PhD project, okay, was actually about measuring Avogadro's number, trying to figure out the atomic or molecular properties of matter as a whole. Okay, doesn't sound much like E equals MC squared yet, does it? Right. So what happened next? What happened was that Albert was trying to do this research project. And for those of you who are familiar, when you are trying to do a PhD, what happens is if you get a fellowship, all right, so it's basically a years-long kind of scholarship, but it's not just like, oh, here's money because you're a good student, but it's rather, here's money to support you so you can eat and sleep indoors while you are doing cool scientific research. Does that make sense? So that's kind of how research fellowships work, or assistantships. He wasn't able to get one. They are relatively limited. I mean, how many places in the world give you free cash just to think and to write cool stuff, right? And it's not that much of it available, even back in those days. So in 1905, right, that was around the time he was finishing his PhD, but in 1903, 1904, thereabouts, he had had a child. He was married. His wife at the time was also a very, very intelligent woman, Elena Maric, and she was a mathematician as well. And so they were trying to make a life of things while he was still doing his PhD. So he got a job supporting the family, right, in a patent office. So he was a patent clerk, basically, in Switzerland during that time while he was working. There have been a lot of sort of romanticized ideals of what that time was. Oh, he was a patent clerk and it was great for him, whatever. It might have been, but basically he was there so he could support his family. This happens today too. A lot of graduate students, they find jobs to support themselves in addition to the work, especially if they don't have a research assistantship or a fellowship. Okay, so anyway, here's Albert Einstein doing that. And so over the course of his PhD time, he's doing a lot of this interesting work. He's thinking creatively. And in 1905, okay, he's 26 years old in 1905. He publishes a whole bunch of amazing stuff. Things just sort of all come together, sort of when people have PhD theses, they sort of all come together. But for him, it was amazing, right? In fact, many people call it the year of miracles for Albert Einstein, because in 1905, he published results about Avogadro's number, right? He published results about something called Brownian motion, which is something you probably learn in chemistry or biochemistry. He published stuff about what's called the photoelectric effect, which conclusively confirmed theoretically why or how it is possible that matter is both, well, not matter specifically, but light is both a wave and a particle. Okay. And he did this thing that today we call relativity. That's something special, not just general relativity. That would come later. He did this thing called special relativity. The paper that he published that was most important on this was called On the Electrodynamics of Moving Bodies. Okay, you've done this already, right? Motion, and then he talked about electromagnetism and things like that. He was trying to figure out why light appears to behave differently from matter, like a matter particle. Let's take this as an example. If I am riding on a ship or something like that, right, and I throw a ball forward, if the ship is riding at 10 miles an hour, and then the ball I throw forward at 30 miles an hour, then to somebody who's on the shore, right, they see me going at 10 plus the ball going at 30. They wind up going at 40 miles an hour according to that person. So relative to me on the boat, right, the ball is moving 30 miles an hour, but relative to the person on the shore, the ball is moving at 40 miles per hour. See, so that's like the relative speeds, how speeds kind of add when you've got particles or objects that have mass kind of moving around in the universe. But for some reason, light doesn't do that. It's a very famous experiment by a team. One guy is named Michelson, and the other guy is named Morley. Okay, this is worth writing down. So I'm gonna write down these guys' names so you can have this in your mind as you're writing down in your study guides and the history of all this that I'm talking about. This, a lot of this you can find on the internet, and there's like the AIP Einstein Project, and his papers are at Caltech and at Hebrew University in Jerusalem and stuff like that. But this is like a very quick, very straightforward summary of that kind of stuff. So I don't want to go too deeply into everything, but you should know this. And then you will be reading more about this and looking at more about this later on in the study guide. Okay, so anyway, let me just do this. Just give you all that information. Okay, Michelson was a guy named Albert A. Michelson. He was a German immigrant to the United States, one of the first recipients of the Nobel Prize. This guy was really, really good at measuring light, okay, measuring how fast light was moving through different media and things like that. Remember, at speed of light in vacuum, 3 times 10 to the 8 meters per second. This guy, Michelson, was one of the first to measure it to any significant accuracy, approaching what we have today. Meanwhile, his colleague, Edwin Morley, was a experimental chemist, very skilled also in figuring out and setting things up, being able to measure things, as it was said, to the 6th decimal place. I mean, really able to measure this kind of thing very carefully. So the two of them together worked on creating something called an interferometer, right? If you remember reading the stuff about light, light interferes with itself, right? When they interfere, you get the sort of multiple patterns that kind of wiggle around. Like if you drop a handful of pebbles in a pond, you wind up with a mixture of patterns, right? So Michelson and Morley were able to take a look at those patterns and measure them extremely carefully to measure things like the speed of a light beam going through a piece of glass or going in one direction or compared to another direction and things like that in a laboratory setup. And what happened is using their interferometer, Michelson and Morley figured out, okay, that light doesn't do the same thing that tennis ball does or that ball does when I throw it. If I am on the boat and going 10 miles an hour and I throw the ball at 30 miles an hour, it's just a gentle pitch, right? This is if I were throwing an overhand fastball, it'd be more like 70 or 80 miles an hour. I can't get a 90-mile-an-hour fastball out of the shoulder, not anymore. But in any case, if I had me going 10 and then I throw the ball, say, well, I said 30 earlier, I'll just stick with 30 miles an hour, soft toss over that way, then someone else would see that ball going at 40 miles an hour if they're standing on the shore. But if I were riding on that boat at 10 miles an hour and I shine a flashlight in the dark and measure the speed of that beam of light, turns out that I would see it going at the same speed as that other person would see it. Yes, that person would see that beam of light going at 3 times 10 to the 8 meters per second. I would see that beam of light going at 3 times 10 to the 8 meters per second, not 3 times 8 meters per second minus 10 or plus 10 or anything like that. In fact, the speed of light appeared to be what we call invariant, right? Didn't change depending on who you were looking. Like if you, as an observer of that beam of light, were moving with respect to that flashlight or not moving with respect to that flashlight, that beam of light would look the same speed to any such observers. Are you kidding me? That's just weird. Light does not behave when it travels like all these other things. And we were talking earlier about how like light is like could be a beam of particles or it could be a wave, right? But surely its speed would behave like any other wave or any other particle, right? You would watch it and you have a relative speed compared to one another. Didn't happen that way. Wow. So people were trying to figure out that for a long time, and they didn't quite have it. They didn't quite know what the right answer was to that puzzle. But eventually, a bunch of people did figure it out. And the person who did it early, right? It's hard to say who like came up with the first of any scientific idea because a lot of people have pieces of discoveries and so forth. They work on over long periods of time. So anyway, Albert Einstein published this thing in 1905, which basically said, I know what's going on. This phenomenon where a beam of light is the same apparent velocity, regardless of what kind of motion the observer is undergoing, is something really worth taking a look at and investigating. And I have the mathematical or physical rules to sort of show you how it works. Okay, so with that, we are now going to go, I'm going to share screen now with you, to chapter 28 of the OpenStax physics textbook, Introduction to Special Relativity. And the reason it's called special relativity is because light behaves specially. Compared with other things that are moving around, light has a special relationship in terms of its motion and its apparent velocity compared with the movingness nature of the targets or the sources and things like that. Okay. Now, what Einstein basically explained was that it wasn't just light that was special. Light is indeed special, but anything starting to move as fast as light would experience special activity as well. And indeed, they followed a relationship that was true whether or not you're moving at the speed of light, except that we can't see it because the speed of light is so much faster than our daily velocities. What we experience seems to be so slow compared to light that we couldn't measure this kind of relativity. So that's why you have special relativity. Now, I don't know about this. The special relativity resemble trigonometry. Both are reliable because they're based on postulates that flow from one another away. Well, special relativity resembles just about anything that's reliable based on postulates, right? Postulates and hypotheses, they're all kind of the same thing. Anyway, postulates are hypotheses that you like say, okay, this is the reality. We're going to go on. Okay. So Einstein's first postulate, right, says that an inertial frame of reference, right, what is it? Read through these things and it's kind of fun, but the laws of physics are the same and can be stated in their simplest form in all initial frames of reference. Okay, all inertial frames of reference. And that had to do with that, remember that electrodynamics of moving bodies to which we referred? Yeah, that was the deal with that. And what happened is we wound up with Einstein's second postulate, right, which was the speed of light thing. Remember that thing I was talking about, right? I talked about the Michelson-Morley experiment. Speed of light is independent of the Earth's motion around the sun. Therefore, the second postulate is written that the speed of light is a constant independent of the relative motion of the source. By using these statements, that the second one is what I was just talking about, right, before I started sharing the screen. What does it mean, right? The constant speed of light is 3 times 10 to the 8 meters a second in a vacuum, and you can move slower in matter, right? So these kinds of measurements are very, very important. So if you have special relativity in this kind of style, right, what happens is that as a result, depending on whether you're moving or not, time and space actually can vary. What? A second is a second is a second, isn't it? No. Turns out that I could experience a second differently from the way you experience the second, depending on how we move. How does that work? Jeez. I was just talking about the flashlights on the boats and things like that, right? So now think about it this way. You and I, we can move, right, in space at different speeds. Say I'm walking in that direction, okay? I'm walking that way. I could walk fast or I could walk slow. So I'm experiencing the length dimension in that direction, right? Either quickly or slowly. I go through it at different rates. What Einstein is saying is that light doesn't do that, but we do. Since we have matter, we have mass, as we experience time, our time experience rate can change also. Are you kidding me? Yes, that's right. So read this thing about simultaneity. What it means is that the idea that two things happen at exactly the same time is not actually correct in the world. Things don't happen at the same time because it's a matter of when you see it, when it stops, and when it ends for you. That's really kind of interesting when you think about it. Okay, so simultaneity is a really odd thing. Go ahead and watch this figure 28.5 and kind of get a sense of what that means. If you're moving on railroad tracks, this person on the street, earlier I was using the boat analogy, but this is using railroad tracks analogy. You're going to see the beams of light traveling, and the beams of light travel at the same velocities, right? Same speed, regardless of whether you're moving with them or not. But because what we see is different, therefore, you're going to wind up experiencing the amount of time from the time the light beam goes from here to there differently from whether a person is sitting on the train or whether you're off the train. Whoa. I know it's like a lot to take, but it's really true. So you get this thing called time dilation, where amazingly enough, when you are moving compared to somebody else, you're experiencing time differently. Okay. In this case, as an example of an astronaut in a spacecraft, right? Notice that the astronaut, because if they were doing the same experiment that you were doing, what you're doing is watching this additional motion of them going that way, right? So you would see time move more slowly when the astronaut is concerned. The astronaut doesn't experience any time difference, but you will, right? So as this person moves, this person will actually age more slowly than you do as you are watching it move past you. Is that amazing? So this concept of proper time, all this math is really cool. You don't have to worry about it for this class, okay? And I encourage you to look at it because it's kind of fun. It's really neat because it's the Pythagorean theorem. It's a squared plus b squared equals c squared. So it's not that hard to do, but it's a geometric way of expressing how the faster you move through space, the slower you move through time. Okay, this is all that, right? And this factor, gamma factor, is different from gamma rays, right? It has to do with velocities. So basically saying that you experience time, the amount of time that goes between two moments, right? If you have an interval of time, you experience an interval of time that's different from the interval of time experienced by somebody else, depending on how fast you or that something else is moving, right? 1 minus v squared over c squared, you take the square root and you put it in the denominator of an equation, and all of a sudden that becomes this relationship between the faster you move through space, the slower you move through time. Isn't that amazing? Yes, there are all kinds of classic examples about special relativity. And a lot of people are like, are you kidding me? How is this possible? Well, I'll stop here, the twin paradox, and I'll get back to it in just a second. Because here's the deal. I feel that one of the most true and effective confirmations of special relativity, that the faster you move through space, the slower you move through time, kind of thing, is an experiment that was done some 60 years ago. Basically, people in the United States at the National Bureau of Standards, now called the National Institute of Standards and Technology, had extremely accurate clocks that could measure precisely the time interval that passes from one time to another, one moment to another, in billionths of a second. You can have really, really, really accurate nanosecond precision clocks. And what happened was they flew them up in airplanes. Yes, they flew one toward California. They flew the other one over the Atlantic Ocean. So, these planes are cruising at 500-600 miles per hour, right? Compared to where you are on Earth. And compared to one another, they're flying like 1,200 miles apart, but they're going fast compared to the Earth. The experiment was they took this plane, they flew them in opposite directions, then they flew them back, and then they landed again. Okay, and so they were trying to see if indeed those airplanes or whatever was on those airplanes actually experienced time at a different rate than we did on the ground. And comparing the special super accurate atomic clocks that they had on the airplanes to the ones that they had on the ground, these scientists showed, indeed they confirmed, that by a factor of just a few billionths of a second, those clocks on those airplanes actually recorded less time passing. Wow. So if you're on a spacecraft, like in a space shuttle, or if you're in an International Space Station or something like that, and you go around at 15,000 miles an hour relative to someone on the ground for like months and months, when you land back down on Earth, you might be several seconds younger than your twin, who might be still on the ground. Yeah. This experiment was also conducted, which is kind of cool, right? In fact, two astronauts who both happen to be twins actually were tested in just such a way. One of the astronauts, I believe that was Scott Kelly, went up to the International Space Station and lived there for a year, moving at 15,000 plus miles per hour around the Earth during that whole year. His twin, astronaut Mark Kelly, he stayed on the ground. And so they measured things of various kinds, like biological heart rates, aging biological systems and chemical systems and like that. But physics-wise, thanks to this special theory of relativity that Albert Einstein helped to solidify, basically showed that Scott Kelly was younger in terms of experience than Mark Kelly by a few seconds. But his body, his biological processes had aged much more than those few seconds. So that's the kind of thing we're talking about. You could ride on an airplane for years and years of your life. You could shave a few seconds off of your aging process, but the amount of airplane food you would have to eat surely would reduce your actual lifespan. That's the kind of thing that special relativity is talking about. And so this idea of simultaneity, right, and the so-called twin paradox, I want you to read about this or watch the videos about it in the study guide that we're referring to. Hope you were taking notes right now, right? The mathematical expression of the twin paradox is shown right here in this section, 28.2, simultaneity and time dilation, the twin paradox. It is super interesting. Weird to think about, but 100% true. Now, what happens is that modern day science, with our technology, we can go very fast. Like I said, we can go more than 10,000 miles per hour, 20,000, 30,000 miles per hour, even if we really, put our pedal to the metal with our rocket technologies. But remember, 20,000 miles per hour is still only about 10,000 meters per second. 10,000 meters per second. How does that compare to the speed of light? The speed of light is 300 million meters per second. So 10,000 meters per second is fast. But what about 300 million? That's way faster. So even on the astronaut speed kind of perspective, the total amount of time being changed, this time dilation, the difference between you on the space station and your twin on the ground, is only going to be a few seconds, maybe a few minutes at most. It's never going to be years and years and years. until we get our technology up to being able to travel as humans, safely at or beyond a few thousand, maybe even 10,000 meters per second, we're never really going to experience that. But years from now, maybe if your twin is going at half the speed of light somewhere, and then turns around after visiting someplace far away and then comes back at half the speed of light and gets back, it won't be just a matter of a few minutes or a few seconds. It might be days, weeks. Maybe if the trip goes on for a year or something, and they'll come back, if they'd been traveling half the speed of light, maybe you would experience a year on the ground. By the time he gets back, he would have only experienced a few months. He would have experienced less than a year by a significant amount. I know it's hard to imagine. We know this is true based on experimental evidence of things like subatomic particles. But you and I, we usually think of age and time not in terms of fractions of a second, but in months and years, right? So someday that will happen when we're traveling super fast. Until then, this is what we do. We understand that it exists and we go forward and we move forward on that relationship between moving in a dimension such as length, width, or height, and the relationship of moving through time. You can change the rate at which you move relative to somebody else. Isn't it amazing? Yes, it is amazing. And it's cool. And it was working these electrodynamic equations of moving objects and getting these special relativistic equations in there that in the midst of doing that work, he was like, oh, by the way, if I do a little calculus and stuff and make some adjustments to my equations in this way, guess what happens? I can take at the limit, if I have something that has very mass, and I somehow get it to the speed of light so that it's moving at the speed of light, it will turn into energy, the equivalent amount of energy of an object of mass m. If you were to take that mass m and turn it into energy, because you're moving so fast that you're getting to the speed of light, the equation is very simple. It's E equals mc squared. It's very, very straightforward. How about that? In 1905, he did this. As a byproduct, as a consequence, it was just a creative thing that he noticed. He was like, hey, I'm going to publish this result and just mention to you all, hey, everybody, this electrodynamics moving bodies stuff is great. And by the way, if you look at it carefully, E equals mc squared. Okay, moving on. And so he mentioned it and goes on and starts doing other stuff. In 1905, he further, Albert Einstein does the Brownian motion thing, the photoelectric effect thing, the Brownian motion, I already mentioned that, the time dilation, right? And its companion thing called length contraction. And he did that Avogadro's number thing. And then he did this equals mc squared thing, all in 1 year, all at the age of 26. Pretty amazing, right? Creativity, extremely important. And that was his year where all this stuff came together, where all his creativity combined with his physics and his math knowledge to produce these wonderful discoveries. Very impressive. He wasn't done though. Turned out, as usual, right? When you get a scientific hypothesis and you make predictions, you get a theory like that, it's like, oh, it works. Then you have new questions and you got to try to repeat and understand new stuff. And here was his point. He's like, wait a second. If I can travel through time faster or slower, the same way that I can travel through space, like left, faster or slower, or up, faster or slower, or forward, faster or slower. Does that mean that time is like length, width, and height? Can't it just be something like a dimension? Is time a dimension? Time is a dimension. By the way, anybody who knows that song, send me an email. I'll give you a point. 1,000,000 points, bonus points. You get up a letter grade. Okay, do it. Time as a dimension. Whoa. That means that the speed of light kind of knits together space and time. That means space and time could be knit together. Now, time is clearly a different thing, right? Because like I can only move forward through time. I can't move backward in time. I can move backward in space. I can move forward, backward, up, down, left, right. Yeah. But I can only go forward in time. I can change my speed apparently as I go forward in time, but I can't change the direction. It's like, that sounds weird. Is there a way to express that mathematically? Turns out he didn't know. So he thought it was cool though. And so as a scientist now, and he's got his PhD and he's got a professorship and so forth, whatever, he decides he's trying to figure out a theory that might actually be able to tie together space and time. Now, time again, it's got to move only in one direction. But if you can figure out a way to knit together a dimension that only moves in one direction, and then three other dimensions that work in both forward and backward directions, and stick them all together into a single mathematical structure, that would be a much more general theory of relativity. It wouldn't just be special anymore. It'd be talk about everything that knit together space and time. So Albert Einstein spent a long time learning new math, learning stuff that he hadn't learned yet in graduate school, new things like how to do certain kinds of mathematical calculations. There's something called tensor mathematics, which was pretty new back in the early 1900s. But he was learning from his friends, and many people think he learned from his wife, also was also a mathematician, right? About these new things, these new ways to make calculations about math. So here he was already, well known as a scientist. He won a Nobel Prize. No, he hadn't won a Nobel Prize yet, but he was heading in that direction. Okay. And yet he was still like doing math, learning math, because he saw something that he wished he had the tools, he had the language to do. It's kind of like, math is just a language in this instance, right? This kind of thought process. Think about it. Let's say I wanted to write poetry in French, right? I wanted to write French poetry. Well, what should I do? I should learn some French first, right? I would write great poetry in English or something, or Chinese or whatnot. But to understand French poetry, I should learn some French. Now, let's say I knew a little bit of French. I want to learn more French so that I can talk about it more. I can learn chanson or things like that. Maybe I'll learn some Italian because I think Italian poetry is really cool. Ognuno sta solo sul cuore della terra. That kind of thing. Why not, right? By the way, if you know that poem, let me know. Bonus point. Million bonus points, up a letter grade. Anyway, bottom line, he did that. And then World War I broke out. And so there's war going on, right? People are fighting on the trenches and they're trying to get territory and things like that. He's in Germany. And in 1915 or so, Germany's winning the war. It's kind of cool. But the scientists were like, nah, let the soldiers fight. I am still interested in working scientifically with people who are on the other side of the war. So scientists in England, for example, and scientists in Germany were still talking to one another. And they're still trying to do good scientific work, despite the fact that their governments were sending soldiers to their deaths fighting each other. Anyway, basically in 1915, 1916, that kind of period of time, Albert Einstein and many other scientists together figured out, and Albert gets the credit for it because he kind of put it all together in a really nice way that was recognized by other people and understood effectively by other people. This idea that space and time actually are together in a four-dimensional fabric called space-time. And that's the concept of the general theory of relativity. And if that is true, Einstein reasoned, and here was the part that extended all of science forever. He said that if this is true, then that means gravity, which has for all this time been mentioned as a force between two objects, is actually the consequence of space and time being warped by things that have mass. In other words, straight lines can get curved depending on where you're looking. Space literally can be distorted. It can be shaped by matter. Wow. That is literally cosmic, right? Here on Earth, we can understand gravity in terms of an acceleration. You've done this already. F equals mc G, right? The force of gravity is mass times the acceleration of gravity, just like F equals ma. But for gravity, that G happens to be that gravitational acceleration of the surface of the Earth, 9.8 meters per second squared. Different planets, a different number. But what Albert Einstein is basically saying now is that that gravitational constant, that gravitational acceleration, right, 9.8 meters per second, it's not caused because there's a pull between the Earth and an object. It's equivalent to a pull. It's exactly the same mathematically, something called the equivalence principle. But gravity is caused by Earth's mass bending space-time in such a way that it induces the motion of objects to zip toward the center of the Earth as if it were being accelerated by a force. So gravitational acceleration is a different thing than force acceleration, like a pull, but mathematically they are equivalent. That is a mind-blowing idea. And Albert Einstein said that this is likely to be true. He published it and he said, here's my prediction. If this is true, if the general theory of relativity is true, then I predict that light itself will bend, because light travels in straight lines when it can. But if the straight line around the Earth has been curved or bent because of Earth's gravity, then the light will follow that path of curved space. Yes, it will. Wow. So guess what happened? He sent out this bold hypothesis and made this bold prediction. He said, yeah, if we could just take a look at stars in the daytime, when you had the sun kind of in the vicinity, then the sun's gravity, right, the mass of the sun will actually cause space to curve around the sun so that light that's kind of off to the side will actually come down toward the sun and then go straight to your eye. It will literally bend the path of light. So that mass, which creates that gravity, will cause the stars' positions to appear different when the sun is in the sky compared with when the sun is not in the sky. That is a fascinating prediction, isn't it? Here's the thing, right? How do you see the stars at night? Because the sun's not there. When the sun is shining, it lights up the sky, right? The light from the sun hits all the different particles in our sky and causes this bluish scattering of light. That's why our sky is blue. And if there are clouds, it's even worse because it blocks it, because then the sky kind of looks white because of all the light that's bouncing off of the clouds. So how are you going to look at the stars when the sun is up in the sky? Herein lies the next step. And this is taking us into the cosmic physics that's going to come in the next lecture. Because here's what happened. There was an astronomer, a theoretical astrophysicist named Arthur Stanley Eddington. Okay, I guess this is a person worth writing down too. Arthur Stanley Eddington he read Albert Einstein's general theory of relativity. This is during World War I. He said, this has got to be tested. This hypothesis is so interesting and so potentially transformative for all of our understanding of the universe that we have to test this hypothesis. How? Astronomers know that there are times over the years when the moon will move directly in front of the sun depending on where you are on the Earth. Okay, the sun, the moon, and the Earth can line up exactly for a few minutes or a few hours at a time. Once or twice every year or so, you might get a little bit of land on Earth, maybe a few miles wide, maybe a few hundred or a few thousand miles long. During that path, if you happen to be there for a few minutes, the sun will be blocked by the moon. If you go to the right place on the Earth, the sun will be not visible. The moon will cast this big shadow. All you can see is the corona, the bright light that surrounds the sun. And then there, it's kind of like nighttime. Not totally dark, but dark enough that you could snap a few pictures and you can see a few stars. Then you can compare that part of the sky at some future time to pictures that were taken when that part of the sky was at night. And then you can see if the positions of the stars are different. Ingenious, right? That is a creative way to test a hypothesis. He was going to test this general theory of relativity. So Arthur Stanley Eddington organized an expedition after World War I was over. In 1919, Eddington and other folks, astronomers, mostly British, but international teams, went to places where we knew solar eclipses were going to happen. Yes, we actually know, by the way, astronomers are very, very good at that. Modern, like even open source free planetarium software, you can put your location down anywhere in the solar system, not just on Earth. You can go to a different planet or a different moon, not even our moon, like somewhere else in the solar system. And you can say, okay, please dial the clock back 2,000 years. What's the sky look like? Or dial the time forward 2,000 years or 2 years or 10,000 years. They will actually be able, that's planetarium software, on your phone, on a computer, in a dome, be able to tell you what the night sky will look like, when the moon and the sun will line up, when all these things can happen. That is how good astronomers are at mapping the sky. And so in 1919, even more than 100 years ago, they knew that there were parts of the South Atlantic, South Pacific, I think it was the Atlantic, but in the south of the Earth, southern hemisphere, where there was going to be a total solar eclipse, where for a brief period of time, for just a few minutes, the moon was going to block the sun. And in that spot, you could take a picture of the sky during the day as if it were dark, like nighttime. They did that. And they measured and they confirmed the hypothesis by comparing the pictures. They showed that indeed the sun's mass created gravity, which caused the light paths to bend. And so the stars' positions looked different in the daytime compared to the nighttime. That was a spectacular confirmation, one of the most famous confirmations of a scientific hypothesis into a scientific theory of modern times. And that actually wound up making Albert Einstein an international celebrity. It was Albert Einstein then who became basically the most famous scientist in the world. All right. Probably up to that point, the most famous scientist in the world was Marie Curie. Of course, Marie Curie is still one of the most famous scientists in the world. She, in fact, is the only person that's ever won both a Nobel Prize in physics and a Nobel Prize in chemistry. Okay, amazing, amazing scientific work that she did over her career. To be able to launch past that fame and become even more famous than Marie Curie, challenging indeed, but that's what happened. And so Albert Einstein, for many years later, and possibly even to this day, is synonymous with scientific discovery, with theoretical thought processes. And I say that he should also be equated with scientific creativity. Pretty amazing stuff, right? I'm going to share my screen no more until you can see where you can take a look and read more about this general theory of relativity thing. But it's not in the OpenStax physics textbook. That's right. It's too advanced for the physics textbook. Even though we're not doing the mathematical side of things, the OpenStax college physics textbook doesn't really talk that much about general relativity. There's some there, no question. But where you really want to go as far as this class, Physics 110, is concerned, is the OpenStax astronomy textbook. And I will show you that right now. So remember, this is going to be the OpenStax astronomy textbook. So here we have see the physics textbook, right? We were talking in the previous lecture about quantum tunneling. So I've left that there. I want you to go to the OpenStax astronomy textbook, Astronomy 2E. You see that? It's the second edition of the astronomy textbook in section 24.1. So you can just type this in. You need to OpenStax Astronomy 2E, and it'll show up on your search engine, and you'll go to section 24. And 24.1, introducing general relativity. Oh, there is Albert, principle of equivalence, right? Can't tell the difference between acceleration due to gravity, acceleration due to a force. And then you go to weightlessness, trying to understand, is it gravity or is it an acceleration caused by a force, right? Oh, space station stuff, great stuff. And then the paths of light and matter. Whoa, great stuff. I want you to read this to get more about general relativity. Okay, you don't have to read it all in detail and everything like that. But here's the key point, right? Matter tells space-time how to curve. Space-time tells matter how to move. That bending, that change, space-time examples. There's some cool stuff here. There's no math that's really described in this section of the Astronomy 2E textbook. So the concept of general relativity is here, and I want you to get it, okay? Take a look. Imagine space, right, is a flexible fabric. This is a two-dimensional version there. Oops. Hang on just a second. I gotta pick that up. Hold on. Okay, I'm back. Thanks for your patience. Although, again, as before, I've said before, you didn't have to wait for very long, but I did have a brief break on taking care of that. So let me share my screen again. Let's finish up this conversation about general relativity, where you imagine that the space-time that we were talking about before, right? Instead of thinking for now, right? Because it's really hard to think about 4 dimensions when we live in a 3-dimensional world. Imagine that the universe where space was actually a sheet, so it's 2 dimensions, and it can bend in this other dimension, which is not this sheet. So this sheet is 2-dimensional, but it can bend in a 3rd dimension. Now imagine if 3-dimensional space could bend in a 4th dimension. Okay, the 4th dimension, dun, 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 you know, something like that. So that's the kind of idea of space-time and gravity. And then you can learn that indeed people tested general relativity. The very important measurements, for example, this thing called the precession of the perihelion of Mercury, right? That's a kind of a thing that Einstein explained using his hypothesis, but then he made a prediction of the deflection of starlight. This is what he showed. And this is that conversation, right? When we're talking about using photographs of things that are in daytime and nighttime, and Arthur Eddington, right? And we talked about May 1919, and it was a triumph, and it made Einstein a world celebrity. So read this if you want the details about special relativity. And then we talk about time, Einsteinian gravity, as a result of the correctness of scientific stuff that the general theory of relativity represents. It really can create clocks to slow down, not just if you're moving close to the speed of light, but to do other cool stuff. Remember I was telling you about atomic clocks and measurements, ground floor and the top floor, to try to figure out things like how different time traveled between the place that's closer to the center of the Earth and farther away from the center of the Earth. And then there was the special relativity testing where you were flying in airplanes and things like that, taken up in aircraft and Gemini space flights, those kinds of cool things. Anyway, that is where we're headed now, because now, thanks to Einstein and all this theory and stuff, we have a connection. We have not just the connection to the material and the matter and the energy and so forth, but we now have connection to space itself. Just like earlier on in the semester, right near the beginning, when we're talking about how Newton's laws of motion, right, knitted together space, motion in the solar system, and things like that, of comets or planets or moons, with the motion of objects here on Earth. Einstein and the general theory of relativity help knit together the relationship between the quantum stuff, the little tiny bits of matter down low, and the overall grandiose structure of the universe, right? So if we are to look at the contemporary theories of the universe today, the kind of scientific mapping of everything that has to do with science or physics in general, this is how I would map it today. Okay, you have on the one hand the quantum theory, right? Quantum physics, or I will say in this case, quantum mechanics, right? The motion of objects on tiny microscopic scales, which leads to how matter and energy relate to one another, right? Matter and energy basically can be explained by the concepts of quantum mechanics. So matter and energy on our scales, on the scales of humanity and smaller, right? Explained with quantum mechanics. Meanwhile, if we're talking about space and time itself, these grandiose ideas, right, about the cosmos, the whole universe itself, therein lies general relativity. The general theory of relativity is the thing that links space and time together, right? General relativity. And space and time, the way that we move through space and time, the way that space and time change because it's influenced by matter, right? General relativity. There's your huge scientific theory, a body of knowledge. And over here is quantum mechanics, a huge body of knowledge. And what holds them together? What bridged that gap? What is it about physics that pulls together all of these great theories that matter and energy and space and time all can talk to one another? It is indeed E equals MC squared. It is the nexus. It is the thing that ties together quantum mechanics and general relativity. So therein, folks, lies this point. We are now ready, now that we know how physics works on these general principles, these large and tiny principles about matter and energy, space and time, we can start thinking about the physics of the universe itself. Have you ever wondered how the universe started? What it's going to end? Why are we in this space? That's physics, right? Now, astronomy is a beautiful science, like I said, which relies primarily on extending the laws of physics as we understand them out into the universe. And how do they experience, or how do they express themselves? So in the same way that we use Newton's laws of motion to express the motions of the planets and the moons and the stars, right? We also use quantum mechanics, right? This thing that is very small, about tiny particles, to understand that with quantum tunneling, things like that, you can generate energy on massive, incredible scales inside the hearts of stars, right? So through that, we extend outward from the physics of us to the physics of everything. And in the next lecture, we will tell you about some of those consequences. What happens when we knit physics with the universe? The astronomical, astrophysical realities that we get out of that, the insights that we get about us and everything around us from that physics. Pretty amazing. Okay, hope you've been doing all your study guides. Hope you're having a great time. If you have any questions, ask me, ask your recitation instructor. Look forward to talking more. Thank you so much. Have a great day. On to the next lecture, which I can't wait to tell you about. It's super awesome. Thanks.